Hello everyone, in this video I'll be going over some Mcat resonance problems. This is for the organic chemistry section, and if you're going to take the Mcat, I think this is going to be a very helpful video because Kaplan doesn't have a chapter going over resonance. I think it's very important to understand. Okay, so question 1 says draw all the valid resonance structures for the allyl carbocation and indicate which carbon atoms share the positive charge. Okay, so I'm going to start off with drawing out the atom. So we have a carbon with a positive charge and then another carbon double bonded. Now, a concept to keep in mind when dealing with resonance is that you are going to be donating to the rich donating to the poor and stealing from rich. So electron poor areas, like in this case, we would donate electrons to there. So in this case, I can bring this double bond over here, and then it can become a structure looking like this. And that basically solves our problem. We have our two structures, and this charge is being shared over these three carbons. Okay, let's move on to 2. And it says rank the stability of the following carbocations and explain why. So the first one is benzyl. So we will have a benzene ring connected to a methyl group with a positive charge. B is an allyl carbocation. It's the previous problem's structure. And then C is a tertiary alkyl carbocation. That is basically a carbon atom bonded to 3 other carbon groups. And this will have a positive charge. Now they're asking us to rank the stability of all of these molecules. So benzyl has a benzene ring. And benzene rings are extremely stable. They are very, very nice for resonance because we can delocalize charges over this entire ring. For allyl, like in the first problem, it has 2 structures. It looks like this. And it's delocalized over 3 carbons. Now the benzene ring will be more stable than the allyl carbocation because this is only delocalized over 3 carbons, and this is over this entire ring. Okay, for C, this will not participate in any resonance. And this is because the carbons connected to the central carbon are sp3 hybridized. Remember that hybridization is basically the jumping of electron through empty p orbitals. So if something is sp3, there is no lone p orbitals, therefore no resonance would take place. So this would be less stable than all of these. I would rank this A, B, and C. Okay, let's go on to 3. And it says between the phenoxide ion and the alk oxide ion, which conjugate base is more stabilized by resonance, and how does this affect the acidity? Okay, so since we're talking about conjugate bases, I think we should draw out the full reaction of how we get these products. So for phenoxide, we will start off with phenol. Looks something like this. And then it reacts with water. And then it will produce phenoxide. And then a protonated group like this. Okay. So remember that benzene rings are extremely stable. So I would guess that this one would be an extremely stable conjugate base. Now, if your conjugate base is very stable, that would make the parent acid very strong. Now, if we look at alk oxide, that is a carbon double bond. Wait, I have an oxygen. Now, if we look at alk oxide, we see that it's bonded to an oxygen and 3 other hydrogens. This will not have any resonance because, again, this carbon is sp3 hybridized. Therefore, there is no lone p orbital to delocalize this charge. So phenoxide is more phenoxide is more stable than alkoxide. Okay, 4 says which resonance structure contributes the most to the hybrid for acetamide, and why does this explain the rigidity of the peptide bond? Okay, so if I draw out the structure, we have a methyl group, a methyl group, and then we have a nitrogen with a lone pair, and then we have a oxygen like this. And I think we can do some resonance here. So we can donate this lone pair over here, and then this will break the bond onto oxygen. So it will look something like this. This would have a negative charge, and then nitrogen will be double bonded, but it will have a partially positive charge. Now the question is asking us which structure contributes the most, or which is the major structure in this case. Is it the neutral form or the form with partially negative and positive charge? So this would be the major one, and it is because nitrogen is less electronegative than oxygen. So for it to hold a positive ion, it's less favorable than its neutral form. And they also ask us to explain the rigidity of the peptide bond. Now, for this structure, we need to make sure that it is a hybrid between these two. The molecule is a hybrid between these two structures. So, if we have a double bond here and oxygen has a positive bond here, we need to remember that double bonds, they can't rotate like single bonds. So if there's a hybrid between these, it cannot rotate. And that's why it's rigid. Okay, 5 says rank the following compounds in order of acidity. So we have acetic acid. It would be an oxygen connected to another oxygen, and then double bond to this oxygen, and then a methyl group. We have phenol, which is just O connected to this benzene ring, and then we have ethanol, which is just this. Now, for acetic acid, we can do some resonance here. I can donate this negative charge over here, and then we can break this bond, and it will look something like this. So basically, we distributed the electron over these two oxygens. And for phenol, we know that if we have a negative charge, we can distribute it over the benzene ring. Now, which one is more stable, phenol or acetic acid? So the answer would be acetic acid, and it's because it's distributing the charge over oxygen atoms. And oxygen is more electronegative than carbon. In phenol, we're dealing with only carbons in this ring. So it's going to be less stable than oxygen atoms doing this resonance, making acetic acid more acidic. So that will be A is greater than B. Now for ethanol, it's a bit more tricky. I think we should look at its conjugate base, and it's going to be ethoxide. It will look something like this, and it'll have a negative charge. So ethoxide, it cannot participate in resonance because the carbon atom that it's bonded to is sp3 hybridized. Therefore, there's no lone p orbitals for it to distribute. So if this is not stable, that means this acid will not be as strong. So the ranking will be A is greater than B is greater than C. Okay, we are on our last problem, and it says which of the following is aromatic? Use resonance and Huckel's rule to justify. So A, it said cyclopentadienyl. Sorry if I'm saying that wrong. Anion. So it will look something like this. We'll have a pentane ring, and it will have a negative lone pair on the top. B says cycloheptatrinyl cation. So it will be a 7-membered ring. with a positive charge, and then C is cyclobutadiene, and it's just a four-membered ring with two double bonds. Now, Huckel's rule is basically an equation to determine whether a structure is aromatic, and it goes like 4n plus 2 equals the amount of pi electrons in the structure. And something to determine whether it's aromatic is that if it's a decimal and it's negative, it's not aromatic. So let's start with A. In this case, we have 1, 2, 3 areas of electron density. That will be 6 pi electrons. So that will be 4n plus 2 equals 6. I can minus 2 on both sides, which will make this 4n equals 4. And then n will equal 1. So in this case, this is not a decimal or negative, so this will be aromatic. Now in B, we also have 3 areas of electron density. That will be 4n plus 2 equals 4, minus 2 on both sides, and 4n will equal 4, and therefore it will be 1 again, and this will be aromatic. Now for C, we have only 2 areas of electron density. So we have 4n plus 2 equals 4. We can minus 2 on both sides, which will make it 4n equals 2. And if we do the math, n will equal 1.5. And because it's a decimal, this will be non-aromatic. And non-aromatic molecules are less favorable for resonance. So that's how it would justify it. Okay, so that is the end of this video. I hope you found this informative. Let me know if you have any questions. Other than that, have a beautiful day.